Okay, let's go ahead and let's get started, folks. I want to start out by just apologize to you folks about yesterday. I had issues with my internet connection. So for you folks at period two, I know it was towards the end, or actually towards the middle. It got pretty chaotic there with the internet cutting out, and then you guys kind of just left um, floating around in cyberspace or wondering what happened. So I want to apologize for that. And then for period three and four, I was trying to work it out. I couldn't get it to work in time. So I apologize for not having class at that point either. I'm going to go ahead and cover the material that we did. For you folks in period two, it may be a rehash of what we talked about already, but I want to make sure that I cover this for period three and four as well. And so I'm going to go ahead and try to cover as much as we can today in this video. And then for tomorrow's video, I'm going to try to finish up with chapter 6 and possibly start introducing chapter 7. We're going to see a little bit of chapter 7 today. So let me go ahead. I'm sorry. Let me go ahead and pause really quickly. I'm going to go ahead and start the timer so that I don't go over my time. But we're going to go over a little bit of what you will see in chapter 7 today. I'm hoping that we can. If not, we'll cover it tomorrow. And my hope then again is to try to wrap things up in the video tomorrow. Thursday, when we meet again, I'll take questions that you may have, but for sure on Thursday, I'd like to start chapter 7 or continue chapter 7 if we get a chance to start it tomorrow, and then review on Friday. And again, the exam for you in period 2, I already mentioned this to you for period 3 and 4. The exam for chapter 6 will be on Monday of next week. So this is kind of your 1 week now, a little less than 1 week's notice on the exam. Okay. So let's go ahead then. And with that said, let's go ahead and get started. Just make sure you understand that if you have any questions, feel free to stop by tomorrow, Wednesday, during office hours. I'll be available. You can ask questions about the video today. I'll have Wednesday's video hopefully posted by 8 in the morning like we did last time. You can go ahead and start watching that. And feel free after watching the video, come by and ask me any questions you may have on Wednesday. But like I said, Thursday I'll make a little bit of time to take your questions about the 2 videos, and then about this video, tomorrow's video, and then we'll start into chapter 7. Okay. All right. Let me go ahead and let me share my screen with you, and let's take a look at this table here. There's one correction that I do need to make. One correction that I do need to make in regard to the labeling here. So let me go ahead then and address that before we go on. Okay, so for you folks in period 2, you already have this, but let me go ahead then, let me address that because there's a slight mistake here. And so with that said then, I pointed out to this table here, we use this table to analyze the numbers and analyze some properties and characteristics of the atom. Okay. All right. So with that said, then this number right here. So let's draw. Let me draw your attention to this number right here. Okay. All right. So this is the electronegativity. This number then is a measure of how well atoms attract electrons towards themselves. Okay. So the idea of electronegativity, this physical property, or this property of atoms that we refer to as electronegativity, this is the ability of atoms then to draw electrons towards itself. So that is its ability to add electrons towards itself. Okay, so this number here indicates then the electronegativity of an atom. Okay, and so this number here is actually a calculated value. We can't actually measure the electronegativity. What we do then is we can obtain the electronegativity from what is called the ionization energy. And so that's what this number means right here. So this is the ionization energy. And so this is a measured value, ionization energy. Okay. And this is what we refer to as the first ionization energy, because this is the amount of energy needed in order to remove an electron from an atom. Now, so these 2 ideas are opposite. If you want to think of it, they're kind of opposite of one another. In one instance, we are adding an electron. In the other instance, we are removing an electron. However, they are related in that we use the first ionization energy in order to calculate for this electronegativity here. Okay, so that's what we have right there. Okay, so ionization energy, is the amount of energy required to remove an electron from an atom. Electronegativity is a measure of how well an atom can add an electron, pull an electron towards itself. Okay, right? So electronegativity here is actually a unitless number. It has no unit. It is a unitless number. Whereas with the ionization energy here, the units then are going to be in kilojoules per mole of atom. Okay? Now, I specify here that this is the first ionization energy because this is the amount of energy needed to remove one electron from an atom. In theory, you can remove all of the electrons from an atom, okay? But it becomes successively harder and harder in order to do so. We'll talk about why when we get to the discussion on ionization energy. However, so the first ionization energy then refers to the energy needed to remove one electron. And that's what we compare. The trend that we're going to compare here is the trend in the first ionization energy. And so you can imagine that the second ionization energy is the amount of energy needed to remove a second electron. The third ionization energy is going to be required to remove a third electron. And you're going to see then that the trend kind of holds. That is, for the second and the third ionization energy, if an atom has a greater first ionization energy than another atom, you will expect then that it will also have a greater second and third ionization energy as well. So we won't look at the trends for second and third ionization energies. We're only going to examine the trend for the first ionization energy. Okay, so that's what ionization energy is right there. Okay. All right. The last thing I wanted to point out to you, the last number then, and this is where I need to make the correction. The last number then here, to the number that's on top, this number here, the last number that I'm going to mention then, this is the atomic radius. Okay. So this is the atomic radius. And again, the atomic radius is a measure of the size of the atom. Okay, so the ionization energy is the amount of energy needed to remove an electron. The electronegativity is the measure of how well an atom can attract an electron towards itself. The atomic radius then is the measure of the size of the atom. Okay? It's measured and it's defined then as the distance, and this is how we're going to define it: the distance between the nucleus and the outermost electron. Now, the technical definition of the atomic radius is the distance is half the distance between two the two nuclei of identical atoms. Okay, so that's how we would technically define the size of an atom. But like I told you on Friday of last week, we're going to simplify it. We're going to say then that the size of an atom, the atomic radius, is just the distance from the nucleus out to the valence electron, the electron that's furthest away. Okay. All right. And I had mentioned then that on Friday that this was measured in angstroms. Actually, this is measured in nanometers. Okay. I'm sorry, picometers. Sorry. So this is measured in picometers. Okay. And remember, and the relationship between picometers and angstroms is 1 picometer for every 0.01 angstroms. Okay? And so that's the relationship between picometers and angstroms. Okay? And so the number here that they're given here, that I give you here then, is in picometers. And so I apologize for that. And so make sure you keep that in mind. Okay. All right. With that said then, let's go ahead then and let's take a look at the trends here. Okay, so if you take a look at the values, let's look at the period trend first. Okay, that means let's take a look at these numbers here and let's take a look at the how they change as we go from right to left across a period. Okay, so there it is. We're going from right to left across a period, and we're going to take a look here first and foremost at period 1. So this is the, I'm sorry, period 2. Okay, let's take a look at period 2 here. Okay. And if you notice then, as you take a look at period 2, the atomic radii do appear, for the most part, if you look at this, to increase as we go from right to left across a period. Now, obviously, there's going to be an exception, and we see the exception here. Okay, obviously with oxygen here, we see the exception, but for the most part, the trend seems to hold. Okay, and that is neon has an atomic radius of 70 picometers, lithium has 152, and so the trend holds for period 2. Now, will the trend hold for period 3? Well, let's take a look at this. Okay, so period 3 then, let's take a look at the numbers here. So period 3, as we go from right to left, so we're moving from right to left across here. Let's take a look at the numbers and analyze this here and see what we have. We have then argon at 98, chlorine at 99, 104 for sulfur, 115 for phosphorus, 117 for silicon, 143 for aluminum, 160 for magnesium, and 186 for sodium. Here, there are no exceptions. We notice, we see that here for period 3. So in period 3 here, the period 3 elements, we notice in that all of them fall into that pattern, okay, that there's an increase from right to left across the period. And then finally, if you take a look at the the last period here, you take a look at period 4, take a look at period 4, okay, and examine the numbers here going from right to left again, examining these numbers going from right to left. And we notice that again, for the most part, okay, the trend seems to hold. We start out with 120 for krypton, 114 for bromine, 117 for selenium, 125 for arsenic, okay? And then we have 197 for calcium, 227 for potassium. And then we do notice then that there are 2 exceptions here, 122 for gallium and 123 for germanium. And so with that said, then for the most part, we still see then the trend holding. So the trend holding, that is from right to left, okay, across a period, the sizes of the atoms will increase with exceptions. And there are going to be more exceptions when I'll show you a more detailed periodic table with all the sizes of the atoms. You can see then, if you look at it more closely, you're going to see then that there will be exceptions to this trend here for a period. Okay? But the trend seems to hold. So with that said, then the period trend, and let's go ahead and write this down. And we saw this on the previous slide. The period trend then is that from right to left, we see then an increase in the size of the atom. That is the general trend for the period. Okay. All right. Let's go ahead then, and if that's the trend for the period, let's take a look then at the trend for the groups. And let's take a look at the group trends. Okay, so let's go ahead and let's take a look at how this works. So let's take a look at group 1 here. So let's take a look at group 1, the group 1 elements. Okay, so we have then hydrogen and the alkali metals. Let's take a look what happens as we go down. We go down the group. Okay, so if we take a look at this here, what do we notice happening? We see then that with hydrogen here, we start out at 37 picometers. We have 152 for lithium, 186 for sodium, and 227 for potassium. It looks like here for group 1, the trend holds almost completely. Okay, so we see then that the size increases as we go down for group 1A. So group 1A, we see that happen. Let's take a look at group 2A. Okay, so the alkaline earth metals, let's examine what we have here. We have then, if we take a look at it, we have 112 for beryllium, 160 for magnesium, and 197 for calcium. And so with that said then, as we go down group 2A, we notice then that the size also increases. And we see that that actually holds pretty well for most of these here. So if we do one more analysis here, let's take a look at group 3A. Okay, we see then that the trend 83 for boron, 143 for aluminum, and then 122. Obviously, there is an exception there, but again, the trend then that will hold for the most part, that as we go down a group, the size will increase. The size of the atom will increase, and that's again what we saw happening with the general trend that I showed you earlier. So with the period trend, size increases as we go towards the left, and with the group trend, then we see then that the size will increase as we go down the group. So that then is the general trend. I think that that becomes fairly simple to understand, and make sure you keep that in mind. Now let's go ahead then and let's analyze why this is the case. So you got to know the trend. You got to be able to identify the trend and remember it. Okay, so you got to remember it, but you also have to be able to explain it. So let's go ahead and let's take a look. And I kind of touched on an explanation for these trends already. We talked about it a little bit on Friday. Let's take a look at it more closely. Okay? Let's go ahead then and let's whoops. Let me go ahead and do this. Let me save this. Okay. All right. So let's go ahead then. Let's take a look at a reason for it. Okay. Let's start out with lithium here. Okay. So if you take a lithium, then lithium has, let's go ahead and write this out. Lithium has 3 electrons, okay? 3 electrons, 2 in the 1s. And so, I'm sorry, if you take a look at, I have here for you lithium, a diagram of lithium with its 2 energy levels, okay? So lithium has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. So we see then, and I'm going to draw in here for you, the 3 electrons for lithium. Now, lithium also has, and let's recall here, it has then 3 protons in the nucleus. So let me draw this a little bit clearer. It's a little bit more difficult. Okay, we have 3 protons. Let's see what colors going to work here. Hopefully, let's try this one. Okay, lithium has 3 protons in the nucleus. So that we want to make sure we keep in mind as we discuss this. Okay. So let's compare this. So let's take a look at the period trend first. So let's compare lithium then to beryllium. Okay, so lithium and beryllium. Remember, beryllium is going to be element number 4, so it's just to the right of lithium. Okay, and so we want to be able to see then why this trend will hold. So beryllium then has 4. Beryllium then has 4 electrons. Okay, 2 in the 1s and 2 in the 2s. Okay, so there they are. There are the 4 electrons that belong to the neutral beryllium atom. Okay, and for beryllium, it has then 4 protons sitting in the nucleus. Okay, all right. Based on the general trend, we know this. We know then that beryllium is a smaller atom than lithium. We know from the trend, beryllium's to the right of lithium. Beryllium's to the right of lithium. We know then that beryllium is smaller than lithium. And just to confirm that, then remember we have then this the size, the atomic radius of lithium is 152. So lithium then is 152 picometers, okay? And beryllium then is 112. So we know then that beryllium is a smaller atom. Okay? Those are the atomic radii. Let's consider why, and you can see it here as well. Okay, let's consider why. Well, we're going to look at, remember, the distance then, what we're going to examine here is the distance from the nucleus out to the electron furthest out. Okay, so we're looking at this distance here, the radius. This radius here is 112. That's the 112. This radius here is the 152. Now, we talked about this, and make sure you keep this in mind. The reason why lithium is a larger atom, is it only has 3 protons that are pulling in on that 1 electron. Whereas with beryllium, you have 4 protons pulling in on this 1 electron. Which what we're saying then is that you have more protons pulling on the electron, it's going to pull it in closer. You have more positive charges here than you have here. You have a greater nuclear charge. And so what we will have here then is lithium has a greater nuclear charge, and the term that we want to make sure we understand then, and you remember then, is nuclear charge. That is the charge in the nucleus, not nuclear power. So don't freak out about that. This is the charge in the nucleus. The charge in the nucleus is greater for beryllium than lithium. Why? There are more protons. And so with more protons, it's going to pull in on this valence electron. It's going to pull this in more. Now, granted, some of you are going to look at this and say, well, there's some repulsion provided from this electron here, but we talked about that on Friday. We said, I had mentioned then that the attraction, the effect that the attraction between positive and negative is going to have a greater effect than the repulsion between 2 like charges. Okay, and so that's why then when we talk about the trend in period, okay, the reason why the atoms get larger and larger as we go towards the left of a period is because the nuclear charge gets smaller and smaller. You have a smaller nuclear charge. And because of that, these electrons aren't pulled in as much. They can spread out further. They can spread out further. Okay, and that's how we can explain the period trend. So with that said, then the period trend then can be explained, okay, because as we go towards the left in a period, okay, the nuclear charge decreases. It decreases, and as a result, valence electrons can spread, can move further away. And that is the reason why we see an increase in the size of the atom as we move towards the right in a period. Okay. All right. Please make sure you understand that. You have to be able. So again, memorizing the trend is easy. You got to be able to explain the trend as well, and we can explain it in terms of nuclear charge. Okay. All right. Let's go ahead then, and let's take a look at. So that's the trend in the period. Okay. Let's take a look at the trend in. Let me go ahead and save this really quickly. Let's take a look at the trend in the. This out. Let's take a look at the trend in the. Oh, I'm sorry. Let me go ahead and do this here. Oops, sorry. In the the group. Okay, so let me go ahead and erase this really quickly. Hopefully you have that already, you guys. Okay, and let's consider sodium. Okay. So lithium is element number 3. Sodium is element number 11. Sodium is just underneath lithium here. Okay, so let's go ahead and take a look at this. That means then sodium has 11 electrons. Let's go ahead and draw those in. We have 11 electrons. We're going to have 2 in the 1s. Okay. We're going to have 2 in the 2p and 6 in the, 2 in the 2s and 6 in the 2p. So therefore, in the second energy level, we're going to have a total then of 8 electrons. 1, 2, 3, 2, 3, oops, sorry, 4, 5, 6, 7, and 8. And then the 1 lone electron is out here. Okay, so there it is. So there are the electrons for sodium. And 2 in the 1s, 2 in the 2s, 6 in the 2p, and 1 in the 3s. Now, with sodium, then, we have 11 protons. With sodium, then, we have 11 protons, and I'm going to write that in here. We have 11 protons. Okay. Now, if we use the same rationale for the trend here, we would expect then that sodium would have a smaller radius. Sodium should be smaller than lithium, but it is not. It is not. And so let's go ahead and take a look at this here. The size of sodium is 186 picometers. Okay? And so what we notice here then is this. We notice then that between lithium and sodium, lithium is the smaller atom. So the nuclear charge on sodium is obviously greater. There's 11 protons. Lithium only has 3, and yet lithium is the smaller atom. So therefore, the trend, the explanation for the period trend is going to be different from the explanation for the group trend. Okay, so for the period trend, the explanation is change in nuclear charge. Okay, you're getting the nuclear charge is getting smaller and smaller as you go towards the left in a period. However, with the group trend then, let's consider what's happening here. The group trend here is a little bit more involved. Okay, so let's go ahead and let's take a look at what the rationale for the increase in size as you go down a group. Because as you go down a group, why does the size increase? Well, the simplest answer first and foremost, there's only one reason for the period trend. Okay, so let's make sure you keep that in mind. The first answer here then, the first reason why then is that you just have electrons that are in higher energy levels. You have electrons in a higher energy level. Here you have this one electron here is in the second energy level. That's going to be N2 right here. Remember, this is N2 right here. This electron is out there in N3. It's at a higher energy level. Okay, and so already that's what we can say. We have here higher energy levels, We have electrons in higher energy levels, thus putting them further away from the nucleus. Okay, so that's the simplest explanation that we can give for why this radius right here is much bigger. This radius right here is bigger than the radius for lithium. Okay, so that's the first reason. You just have electrons in higher energy levels. Okay? But there is a second reason that is more technical, but it actually is more correct. Okay, and that is a phenomenon that we refer to as shielding. Okay, now shielding helps to explain why the nuclear effect here, okay, the nuclear charge here, doesn't affect this electron as much. Okay, even though you have 11 protons, there's a reason why these 11 protons can't pull in on this electron as much. Okay, and it actually can't. And what is this idea of shielding? The way that I like to imagine, I like to present this idea of shielding is that imagine if you were sitting around a campfire. Okay? So this is the campfire here. Okay, and so if you are sitting right next to the campfire, the closer you are to the campfire, the more intense the heat is that you will feel. Okay, so you can imagine then if these two folks here, they're sitting right next to the campfire, it's going to feel hotter. Okay? Now this concept of the campfire works very well with the period trend here. The beryllium campfire, 4 protons, it's going to be much hotter than the campfire set up by lithium, or with only 3 protons. So therefore, this one electron here, this electron here is going to feel a much more intense heat. It's a stronger heat that reaches this electron than this one. And therefore, it's going to, and so if we relate it back to being pulled in, this is going to be pulled in greater because the intensity of that pull is going to be greater. Okay? Down here then, the intensity of this flame, we're at 11 protons. We are at a very intense flame. Why is it that this electron doesn't feel as much heat? Because first of all, it's further away. It's a higher energy level. But secondly, if you can imagine, so these two folks here, let's imagine this, let's continue on with the campfire analogy. These two folks here will feel the greatest amount of heat. First of all, they're right next to this very big flame, okay, and there's no one blocking their way, okay. As you move back to here, okay, you have then these 6 electrons, these 6 people sitting on the second ring on the outside, they still feel a pretty intense heat because there's only two electrons, 2 people blocking the flame here from them. So these 6 people here will still feel a pretty intense flame. However, this one person, okay, will not feel as much, will not feel the intensity of that flame as much, because you have then not only 2 people, but now you have these 6, you have 8 total blocking the flame, blocking the heat of the campfire from reaching this one poor soul way out here. And so this one poor soul way out here gets cold. He or she doesn't feel the heat as much because he or she is being shielded from the flame. Okay. The same thing holds true here when we talk about shielding with electrons. Yes, there are 11 protons here, but the 11 protons here, this one electron doesn't feel very strongly because it is shielded by these 8 electrons here. And that is how we can explain why the period, the group trend, group trend here. So the group trend here, as let's go into, as we go down, okay, we have electrons in further away in higher energy levels, and are thus further away. Okay, so that's one reason. And then secondly, shielding increases as you go down a group. So two factors explain why the size of the atom gets larger as you go down a group. First, you have electrons that are further away, they're in higher energy levels. Okay? And second, you have greater shielding. You're adding more electrons in between, and so the shielding will also increase. The shielding here doesn't play too much of a factor, because if you notice here, for the period trend, each of these electrons here, let's just focus on this electron and this electron, they're being shielded by the same number of electrons. Okay, so here you have 2 electrons shielding this one electron. Here you also have 2 electrons shielding this one electron. Shielding doesn't change across a period. Shielding changes as you go down a group. And that's what you got to make sure you keep in mind. Okay. All right. So there it is. So now we have a basis for an explanation for the period trend. Okay. And so we have then the period trend here and the group trend here. So please make sure then that you are able to understand this, okay, and be able to explain it. Okay? And so that is how we know then that there will be, and that's how we can explain then the differences in the sizes as for the different atoms. Okay, so that's how we were able to explain it. Okay. All right, very good. Let's go ahead then and let's take a look then at. Oops, sorry. So the graph here basically gives us this idea. So it lays out for us, if you take a look at it, and let's just quickly summarize this. Okay? So we basically analyzed the numbers here. So if you take a look at this, this is basically right here. If you take a look at all of these elements here, if you take a look at elements I have for you here, lithium, sodium, potassium, rubidium, cesium, and francium. These are all, and hopefully you recognize this, these are all group 1A elements. And if you notice here, the trend generally does get larger, bigger and bigger as you go down group 1A. So you start out here with lithium being the smallest of group 1A, and then it gets bigger as you get to francium. Okay. And if you notice here, this is underneath here, we can see the same thing for group 7A, and hydrogen here is obviously down here. But if you take a look at group 7A here, these are the halogens. Okay. And if you notice then also with the halogens, we see then that this is group 7A. Now for the most part, I'm sorry, not polonium, just through iodine, sorry, through iodine. Okay. If you'll notice then that the size tends to also increase as you go from fluorine at the top down to iodine at the bottom. Okay, so those then would be your group trends there. And if you follow here, from lithium to fluorine, this then is going to be your period trend right here. And I didn't highlight it for you, but hopefully you notice it from lithium to fluorine. This is going to be your period 2 elements right here. So if you take a look at this this part of the graph right here, let me go ahead and highlight that for you. Okay, if you take a look at this part of the graph here, okay, that will indicate then that is the period trend, and this is period 3. Okay. So lithium being the largest, going down to fluorine being the smallest. So as you go from right to left, so fluorine is going to be at the far right of period 3, towards the left, the size will increase right there. Okay. All right. And so for the group trend, it's going to depend on the protons, the nuclear charge, and that's what you want to make sure you keep in mind. Okay. And oops, let me say this. And if you look at the within a period, the number of electrons being added, same energy level. Okay, and the I'm sorry, with the group trend here, you have then the electrons being added to greater and greater energy levels that are further away, and that the shielding is going to increase within a period. Then the shielding stays the same, but you have then more protons. More protons, the nuclear charge increasing as you go towards the right. Okay, and that's what makes it smaller. Okay, all right, very good. So if you take a look at, here it is. Here's the table I was telling you about. So this is the full periodic table. You know, for the one that I gave you, the chart that I gave you before, we remember we had the group A elements. Okay, and so here you take a look at the full periodic table. You do notice that in general, the size does get the largest. So if you take a look at let's see, 1, 2, 3, period 4 here. Potassium's at 227, krypton is at 122. And if you notice then when we get to gallium to zinc, I mean, there are going to be differences here. I mean, if you take a look at the group B elements, and this is why we kind of left it out, you see there's more variability the group B elements than we see with the group A elements. Okay, but the trend, that's what we want to look at. The trend seems to be fairly consistent. It seems to hold for the most part. Okay, and if you notice then, let's take a look at, we already saw this, as we go down, group 1B here, the size tends to get a little bit bigger, and then you have these two being the same. And so, like I said, the general trend then is going to hold. Okay? So with that said, you can say then that probably the smallest atom, if you follow the pattern here, is going to be helium. Helium's roughly, but yeah, actually hydrogen is going to be the smallest atom. But if we follow the trend here, we can, if we keep this in mind, it'll help you. The elements in the far right-hand corner here will be the smallest. The elements in the bottom left-hand corner here will be the largest. Okay, again, with hydrogen being an exception, hydrogen should probably be over here with helium. Okay, all right. So that's going to be the group and period trends for atomic size. Okay? So what I'd like you to do then, real quick, and you won't need to write this on your paper. I would like you to take a, let's go ahead and take a look at this here. Let's take a look at number 13 here in your problem set. And what I'd like you to do then is, and I'll make sure I indicate the directions here on the Edpuzzle, is just type in your answer. You don't have to write it out on a separate sheet of paper this time. Type in your answer. I want you to arrange these atoms here in size from decreasing atomic size from largest to smallest. Okay, so go ahead and write. Take about 30 seconds. 30 seconds. I don't think that should take too much longer. 30 seconds to put these four atoms in order from largest to smallest, and then we'll finish up with this. Okay, so largest to smallest. Let's go ahead. 30 seconds. Okay, let's go ahead then and okay, let's go ahead and let's do this. So if you notice then aluminum and these are all going to be appearing in the same period. These are period 3 elements. And so you just have to put them in order. So we're going to go from largest to smallest. You just can put them in order from left to right as they appear from left to right. So the one furthest to the left is going to be sodium. The sodium then is going to be the largest of these atoms. Aluminum comes next, and so that's going to be put there. Sulfur and then chlorine is furthest to the right, and therefore it will be the smallest. Okay, so if this is then representing a period trend, so this is a period, and it's going to be the period 3 elements. So sodium's furthest to the left, it's going to be the largest. Chlorine is furthest to the right, it's going to be the smallest. And so this is the period trend here. Okay, all right. Very good, folks. I hope that we can get a little bit further with the discussion today, but that's all right. You know, what we'll do then is on Wednesday, tomorrow, I'm going to talk about the ions and what they are, and then we're going to talk about the trend in ionization energy. Okay. All right. Very good, folks. Have a good rest of your day. And then again, you don't have to post anything for this video here on Google Classroom. I'll just check for this answer here on Edpuzzle. Okay. Have a good rest of your day. Have a good Wednesday. Please make sure you watch the Edpuzzle video on Wednesday as well. And then I will see you folks on Thursday. Again, if you have any questions, stop by tomorrow during office hours and ask them. Okay. If not, I will see you folks on Thursday.